taken from, inspired by Schaumann and Van Valkenburg's design of analog filters. It has the adjustable 1 to 30 kilohertz through manipulation of resistors G1 and G2. These are a dual-ganged potentiometer. So it can shift anywhere from 1 to 30. The specifications were inspired by the Duo 773 commercial electrometer, and the maximally flat passband gain was chosen to maximize ideal response for rejection of unwanted noise and passing of uniform sensitivity for wanted frequency. The DC gain can also be adjusted via a trimmer potentiometer at RB. For our purposes, it's set to maximize our specifications. The low-pass filter realization here, we have overlays of Bode plots between our measured results of our circuit as well as our simulated results. The simulated results were achieved through use of the LT Spice simulation software. These are graphs showing the trend from the low pass filter while at a 3 dB of 1 kilohertz and a 3 dB of 30 kilohertz. We were not able to fully achieve the minus 40 dB per decade.
Did we lose a little audio?
Yes, we no longer have audio.
Can you hear us?
We can hear now.
Oh, great.
Fantastic.
So we missed about a minute. We missed about a minute.
Okay.
Yeah,
I'll just re-explain this then, since I'm not entirely sure. Sorry about that. We were having some network issues. So this is the overlay realization of the Bode plots of the simulated versus measured for our system. The simulated was from the LT Spice simulation software. We could not reach our specification of minus 40 dB per decade due to the limited gain bandwidth product of the LM741 operational amplifier that was used in this project. Simulations showed that using a operational amplifier with a higher gain bandwidth product will alleviate these issues.
The purpose of the notch filter was to reduce noise from the 60 hertz frequency of the building power. The topology seen in the circuit is a state variable filter used from a website called Basic Electronics Tutorials. This topology was ultimately chosen for its ability to adjust the frequency, the gain, and the quality factor all independently. The picture on the right shows the realized circuit built on the breadboard. Here, you can see an overlaid Bode plot of the measured versus simulated results. LT SPICE again was used for simulations. You can see that the tested or measured notch depth didn't make the specified minus 60 dB, but instead we achieved about a minus 40 dB. We suspect this was due to component tolerance, as minor deviations in resistance and capacitance will adversely affect either the notch depth or the notch frequency. This was also observed in simulations of in LT SPICE. To mitigate this, we added small trimmer potentiometers in series with some of those resistors. The anti-aliasing filter was developed to prepare the signal for an analog to digital converter for a future digital signal processing board. The 13 kilohertz 3 dB frequency was inspired by the Duo 773 specifications. It was relaxed to the 13 kilohertz frequency to reduce the filter order and in turn reduce the cost and complexity of the filter. The minus 60 dB per decade attenuation and minus 60 dB at 48 kilohertz specifications allow for a 96 kilohertz oversampling to reduce error. The sixth order Sallen-Key low-pass topology was used from an online filter tool referenced below the schematic and modified in LT SPICE. The assembled circuit can be seen on the right. Here you can see a Bode plot overlaid by the measured and simulated results. We ran into issues reading high frequency, high attenuation output voltage, which is the reason it stops where it does on the Bode plot. We observed in LT SPICE that this attenuation does meet the specification, and when comparing it with the pattern of the testing results, we can verify that the specifications can be met.
After testing, we were able to meet most of our design specifications, as the validation table below will show. The low-pass filter was found to have a variable 3 dB frequency between 1 and 30 kilohertz. It was also found to have a maximally flat gain in the passband. We were unable to reach the negative 40 dB per decade attenuation due to the limited gain bandwidth product of the LM741 operational amplifier. The anti-aliasing low-pass filter was found to have a negative 60 dB per decade attenuation and a 3 dB frequency of about 13 kilohertz. The anti-aliasing filter also approaches negative 60 dB at 48 kilohertz. The notch filter's notch frequency was measured to be 60 hertz, but we were unable to achieve a notch depth of negative 60 dB. We initially set a goal of keeping the total cost of the project under $250. After purchasing our components from both DigiKey and Amazon, the overall cost of constructing the instrument was $58.72. This total does not include any cost associated with the manufacturing of any printed circuit board. As you can see, we are well within our initial goal. The KeyCAD software suite was implemented to perform the schematic capture and develop printed circuit board layouts under the Creative Commons license for future expansion of the project. All three filters seen here have been laid out on 1.6 millimeter thick 2-layer boards. The component values and footprints were retrieved from online libraries curated by KeyCAD and DigiKey. KeyCAD's default trace width of 0.25 millimeters was used for all external traces. We chose this because we knew that we would be exclusively dealing with nanoamp level currents. The cost of having a board house manufacture the boards was found to be about $55, bringing our total project cost to $112.72. So we are still within our original budget. We would like to conclude our presentation with some recommendations and observations. Our first recommendation pertains to the component tolerances of the notch filter. We would recommend the purchase of components with tighter tolerances for anyone who wishes to build on this project. We understand through simulation that plus or minus 1% or lower tolerance components would be ideal. Although this will increase the cost of realizing the circuit, there is enough room in the budget to justify this expenditure. We would also like to recommend the investigation into the use of alternative operational amplifiers. As previously stated, the gain bandwidth product of the LM741 inhibited filter operation at higher frequency. After simulation in LT-SPICE, we have found that the LT1115 operational amplifier has sufficient gain bandwidth product for our higher frequency application. Lastly, we would like to remark on the importance of lab access for this project. We have had limited lab access through the COVID-19 pandemic and feel that more time in the lab would be very beneficial for anyone continuing this project. This concludes our presentation, and we would now like to open the floor to questions.
Okay, any questions for this group? Dr. Miller, any questions?
No, I would like to point out that this group, they did a nice job on the project. Their sponsor kept changing the specifications on them, which is something you're never supposed to do in senior design projects. So I wanted to mention that.
Anybody else? If not, let's give this group a virtual applause. And thank you, gentlemen, for your presentation. We will rejoin after I turn off recording at 11 o'clock.
Thank you very much.
Thank you.